and thanks for coming. You know your exam's in a couple days. I guarantee even some of the new material that we go through will have 2 questions in it that could be on the exam on Thursday night. So we will get some good practice and review through our lecture today. Your labs this week will also be doing hypothesis testing about a proportion with you, and then some other exam 1 review. Just as a heads up for next week, there are labs. You get your exam back, and you'll be going over module number 3. And our material that we covered today is where you'll see module 3 in a simulation of what we talk about today. There is no pre-lab for next week, but there will be one for the week after break. So we'll have that one up and ready early. So as soon as the exam's over, you can get that done before you go on break if you'd like. All right. We will get to a little lecture review today. I hope you brought that sheet with you. If not, you'll be able to follow along and bring it on Thursday. And let me see if you have a question or comment at all first before we turn to some material. Question or comment? Yes? Disjoint and independence. Bring that question up if I don't remember when we turn to the review time. Definitely. Any other questions or comments? We're going to do our little bit of new and then some review. All right. Does this work? So you know where to go on Thursday night? You know what to bring? Don't have to bring too much, but do bring an ID, things to write with. Make sure your calculator's not getting low on batteries. We sometimes have a calculator as a backup in the exam bins, but not enough for everyone. I've even had some students arrive without a calculator at all. No, you would like one, just to have, do a few calculations. All right, first question is a clicker question. To get us back on track on where we are or what we had done already. So you are asked in this question to identify the 2 parameters that we have already focused on. We have gone through how to estimate those parameters with the confidence interval and how to test theories, hypotheses about them. You are asked to identify the parameters as opposed to what? The statistics. It's about a 70-30 split right now. And although one of those parameters you won't be tested on Thursday night, the other one you will. And there's still about 12% of you who are getting it backwards. Better, all right. But indeed, which ones are the parameters? A, P, P1 minus P2. These other guys down here in B, those are the statistics. We have learned how to estimate the true proportion P with a confidence interval, a range of reasonable values. You've learned how to test theories about the population proportion P. You've done 2 tests, the large sample z-test and the small sample binomial test, where you have that data check on whether your sample size is large enough so you know which one to do. We have also gone through the same inference techniques, confidence interval estimation and testing of theories for the difference in 2 population proportions. For that parameter, we only handled the large sample case. We did the z confidence interval. We did the large sample z-test together last time. That is what the homework 4 that will go up on Thursday will be about, just the 2 parameters, P1 minus P2 inference. We're going to have homework be up on Thursday morning and due every week from here on out on Thursday night at 5. Just to give you one more day past labs, and it still works to have the GSIs discuss it with me when we have our weekly meeting after they've closed out, so it works fine. I know you won't even look at that until after the exam, but it will be there, and it's just on the one new proportion, P1 minus P2 parameter. Which would be your answer, A or B, if I asked you Identify the quantities that have a sampling distribution. That would be B. What kind of things have a sampling distribution? The statistics. Those quantities that are based on a sample results that would vary from one sample to the next, or from independent samples to the next for the two proportions. All right. We're moving on to page 107. We're moving on to what if the response is not yes or no, success or failure. We've handled the inference techniques for the categorical side when it's two outcomes, yes or no. Page 107 introduces us to the idea that sometimes your response is quantitative. You want to learn about the average height, the mean reaction time, the average score on that test after trying a new teaching method out. So the new parameter that we're going to be studying, not proportions, not p's anymore, but rather means. And we're going to be looking at the population mean. You've learned that symbol mu to represent the mean of a population. When it was the mean for a variable whose model describes what's happening in the population, we also had that E, right? Expected value of X, or the population mean. So we have this population. Inside the population are everybody's reaction time to some stimulus. We want to learn about the true mean for that population, but we can't look at the entire population. We again will require a random sample to come out, and we'll calculate on those reaction times we have in our data the mean. The mean from our sample is not mu. It is represented by what? X bar. X bar is our sample mean. It is our new statistic that we will study today on how it varies from one sample to the next. There's a background on that page 107. We've actually looked at these results in a different way before. It was a study of full-time workers, asking them about how many hours they work per week. When we introduced proportion, we said, do you work more than 40 hours per week, yes or no? And we looked at the proportion who said yes, they do typically work more than 40 hours a week. Here we actually recorded the number of hours they typically work per week, that quantitative response. It was a probability sample that was selected of 1,000 workers, and the mean for that sample was 43. We can identify again the key parts to this inference scenario, the population versus the sample. Those would be the same as what we had before. For the population, we were trying to learn about all full-time workers. And this was a study conducted just in the United States. Couldn't possibly survey all of them, so we took a probability sample, a sampling technique that involved randomness. And that sample consists of then how many? The 1,000 workers that were surveyed or polled, and whatever their responses were. That's our sample. I have x1, x2, all the way up to x1000. All of those values were recorded. The parameter, what I'm trying to learn about for the population, is the mean. And the Greek letter mu represents the population mean. The population mean, number of hours worked per week. This would be for all workers. Just like Thursday night, if there is a P that you have to define, because you're testing a theory about that proportion, you're going to call P what? You're going to say it is the population proportion. Make sure you identify it's not just the proportion, because we have P hats versus P. Identify it's the population proportion of successes for all people who receive a certain treatment or whatever it might be. The statistic, on the other hand, is what we do calculate based on our sample, and we'll be getting a sample mean x bar. The sample mean number of hours worked per week And in the description of this study, it says the mean was 43. Is that mu or x bar? This 43 here that was observed came from our sample, so it is x bar. For our sample, x bar turned out to be 43. Now what about mu? Does mu vary, or is it fixed? It's fixed, just like your proportion p is a fixed number. That's why we don't talk about 95% of the time p will hop into your interval that you already have done. P is fixed. It's a fixed number, just as mu is a fixed but unknown quantity. So our parameter here is fixed but unknown. Our sample mean of 43 is known once you take the sample and look at it, but it would not be fixed in the same value every time. From sample to sample, it would vary. So let's answer those couple questions at the bottom of that page. Can anyone tell me how close is this 43 that we got to this true mean mu? How close? How accurate was this particular estimate we got, 43? How close is it to mu? Can you calculate that distance? No, because you don't know mu. You can never say how good your one estimate is, but we will be able to quantify how good sample means tend to be at estimating mu, how close they are to the true mean mu on average. So we can't say how close any particular one value that's observed is to this unknown mean mu because mu is unknown. We have no idea if it's within 3, 4, or any particular distance from that true mean. What happens if we were to take another sample of 1,000 workers from the same population using the same probability sampling technique? Will we get the same value, 43, 43, 43 every time? No. We might get a 43 again at some point, but it's going to vary. It's going to vary from one sample to the next. So how will it vary? Is the sample mean going to vary all over the place? Do we hope it varies really close to mu? And that its variability around that true mean mu might not be too much, so we can be pretty confident in our results when we do get them? We're trying to understand what are the possible values for x bar if we were to think about taking samples over and over again. What would the distribution of x bar be? That is the sampling distribution. When you talk about a sampling distribution of some statistic, you're trying to decide what are the values that statistic could take on if you took samples over and over. What are those values and how often do they occur? You have learned about a couple of sampling distributions already, for p hat and for p1 minus p2 with the hats. What did both of those sampling distributions turn out to be, approximately, if you took a large enough sample size or sizes? Bell-shaped. And here is another statistic that's going to turn out to be bell-shaped, either exactly bell-shaped or approximately. The results are on page 108. Again, just some definitions at the top. The true mean. And then there is this true standard deviation. I mean, imagine the population of all scores on some exam for all students that would be taking it. There is a true mean for that population. There's a true standard deviation that reflects the variability. And then there will be this sample mean that comes out based on taking a certain sample from that population. Think about all possible random samples being selected, and therefore getting all those possible x bar values being computed. The first time we get an x bar, maybe it's 43 like we did. If we did it again, maybe the sample mean would be 42.8. Maybe the next one would be 44.1, and so on. Imagine all of those sample means being calculated if you were to take the time and go back and sample 1,000 workers over and over. Here are some results that will happen if you did that process. If you took all those sample means and averaged them all out, they would turn out to be, as an average, equal to mu, the population mean. Any one value of x bar may not be mu. Might be above it or below it, but they tend to average out to mu. That property tells us that this particular estimate, the sample mean, is an unbiased estimate. In other words, we would expect, on average, sample means to be mu. The expected value of the sample mean, what you'd expect the sample mean to be if you averaged across all those values, is mu, unbiased. P hat was also unbiased, because when you drew your curve for the model for P hat on your homework, you centered it at the true proportion P. So it was an unbiased estimator too. So on average, it's right on, but of course, some of these values will be off. How far do they tend to be off from the true mean? Not for any particular one, because I don't know mu, but on average, can we quantify what that distance might be? You have the result. The standard deviation of all of those x bar values would end up being the original standard deviation that you had in your population. So it does depend on how variable the results are in your population, but it also depends on how much data you took, your sample size. And that goes in the bottom. Isn't that similar to the standard deviation that you have for p hat? What does that one look like? P, 1 minus p over n, the square root. So the n's on the bottom. That's why it's a good estimator, again, because if you took a larger sample size, what's going to happen to that standard deviation? Bigger sample size means the standard deviation smaller. Is that a good thing? We usually want less variability so that our estimates, our sample means, would tend to be closer to the truth. So this is that true standard deviation. So we know where it's centered at. We know now the give or take, this particular new standard deviation here. We need to know the shape. And as we already mentioned, what shape tends to come up a lot in statistics as a model for a lot of statistics? The bell curve. Averages tend to vary normally. There are two ways we get to that bell curve or normal model, and we have them through a couple pictures here. The first result I call the exact result. It requires a little bit more. It requires that your original population of x values, your response, scores on a test, reaction times, that this population of original x values is normally distributed. So scores on the exam are bell-shaped, or reaction times are bell-shaped. And of course, there'll be some mean and some standard deviation. So this is the model for your original population of values. You have to assume it's normal with some mean and some standard deviation. You don't know the mean and standard deviation. You're going to be estimating that, but assume a bell curve would be in a reasonable model. You want to learn about the true mean? So you take a random sample, and it can be any size at all. Does not have to be large. It can be just 5. You compute the sample mean, get your x bar. Consider writing that x bar on a ball and throwing that ball into this new basket. This new basket is the population of all possible sample means. All possible x bar values. If you were to do this process, and here's the picture of that process, go to your population, take your sample randomly, calculate x bar, throw it on a ball and put it in that basket, and keep doing that over and over, all those x bars. What's going to happen for the model here? We already know the mean. What does the average of all the x bar values end up being? Just mu. What was that new standard deviation that we just determined? Averages aren't just sigma anymore, but sigma over the square root of n. Averages will vary less from the true mean than individuals will. And then we also get, as an exact result, that the model over here will be normal. If your original variable, your response that you're measuring, is a normal model for it, then you'll get normality for x bar no matter what sample size you take. Don't need to have a large sample size for this result to work. So that's one way we can get to our normal model that we will use to do our confidence interval and our testing a little bit on Thursday and next week. Here's the other way we get to it, the more useful way, because you make a QQ plot of some of your data, and it's not always going to be a bell-shaped model that it follows. But you can still get to the point where you need to, provided you take a large enough sample size. So your original population of all x values, all scores, all reaction times, maybe it's not necessarily normal. Maybe it's quite skewed to the right for income data. But there is some mean, and there is, of course, some standard deviation still for your responses. But the model, the picture of that density would not be normal. I still want to learn about this mean, though. And I take my random sample. And if I take my sample large enough and compute the mean, and think about all those values for x bar, what do you still get for the model of this population of all x bar values? You're still going to have mu as the mean. X bar values will always vary around the true mean mu, whether you take a small sample size or a large one. You get that unbiased property. And sigma over the square root of n will always be what the standard deviation turns out to be. That's provided you take random samples. That's all you need there. But over here, we will still be able to use a bell curve. It won't be an exact result. It'll be an approximation. But we'll still have a normal model over here, even though the original population wasn't normal at all. This is a very famous result. One of the most famous ones, called the central limit theorem, abbreviated sometimes CLT. So you have, when you think of a random sample, IID. We say we have a random sample, you've got independence, you've got identically distributed. We have, if they're a probability about an and they're independent, what can you do? Multiply. And now we have this famous CLT, central limit theorem. Now there is a question we still need to ask, because this is a different scenario. This is not proportions where there's an n times p and an n times 1 minus p check. There's no p anymore. I need to know what n is large enough. And now this is a strict value, not n times p being checked. And there are a couple different books that vary in terms of what's really large enough. I've seen anywhere from 25 on up. Some books are pretty strong on 30 or more. I've seen simulations in both of those ranges. We'll assume 25 or larger. Your book, I believe, starts with 30, relaxes that a little bit later, and the simulation you do with Module 3 next week, the largest sample size you can pick with that simulation is 25, and it works really nicely. So because you'll see it with 25, we will go 25 on up. It really isn't a strict cut that as soon as you have, 24 is not enough and 26 is, but actually it's a continuum of values, and it depends on how non-normal the original population is over there for how large you really need. But there's our result. We're going to use it. Here is the way it looks on your yellow card on the next page. This is the bottom right corner of your first page of formulas. You do not need to know it or use it for Thursday night, but you will for future homeworks and such. These first two results hold for any sample size. All you need is a random sample for you to get that the sample means will vary around the true mean mu, that their give or take is sigma over that square root of n. Then you've got the sampling distribution results, and there are two of them, just like we had our two pictures. The first one I kind of call the exact result, result number 1, because it requires what? It requires you start with a normal to get that normal for x bar. The other result, the CLT, is an approximate result. Does not require you starting with a normal, but it does require your sample size being large. The exact result just says as long as you've got a normal model already, it doesn't take anything then to get to the normal model for x bar, no matter what sample size you take. But if you don't have a normal model to begin with, then the larger the sample size, the more bell-shaped that original X-bar model turns out to be. So let's try out a couple questions. You've got ACT scores here. You have a normal model for ACT scores. You've got a mean, 18.6, standard deviation, 5.9, not real nice numbers, but that's the model that holds for these scores. So right now, before we even go to the questions, 18.6, what symbol would you use to represent that? It's a mean. Is it mu or X bar? You have a normal model, a model that describes the population of all ACT scores. When you think of your distribution notation, you write an N for normal, and then you put what, 18.6 here, and 5.9, and what do those two things represent? The mean, mu, and the standard deviation, sigma. Nothing was stated that we took a sample, and here's our mean of our sample, that would be X bar, but rather, here's our variable ACT scores. The model for that variable is given to be normal. Then here's the mean, the true mean mu, and the standard deviation. Now, questions A and B could be asked on Thursday night. I'm going to let you work on those for a couple minutes. If you want, get your calculator out, because calculating that z-score is not as easy in your head with these values. But try it out, talk with your neighbor. A and B could be on the exam, but not C. We'll do that one together. Give you a couple minutes to try it out, and we'll gather back. All right, let's see how you're doing. ACT scores are normally distributed. That's all you have is a normal model for your variable x, your random variable. So we can talk about how likely is it that the next selected student is going to score 21 or higher based on this model. When the model is normal, you just have to get a z-score so you can relate the area you want for this normal curve to the areas that are under the standard normal that you have to work with. The minimum work that I would really like to see on the exam is at least tell me how you got your z. Because I'm seeing some of you round it to 0.40 versus 0.41, because it is in between when you calculate it. Your z-scores on your table only go out to the hundredths place. So you're going to want to get it to the closest hundredths, and that would be 0.41. But I know on my guidelines I would probably have, if they use 0.40, here's the answer and no penalty. All right? I'm only rounding to the nearest hundredths here. I'm not rounding to a whole number. We wouldn't do that unless it's a sample size issue. But 0.41 is my value of z. Now I would have some students put 0.41 as their probability answer, because it's between 0 and 1. But I have to take it still to the table, right? You're looking at the z-scale, and you get that 21 is only 0.41 standard deviations above the mean. And if you look at 0.41 in your z-table, you get what, 6591? And I know that that can't be the right answer because of my picture. My picture shows me it must be less than 50%, just by what I shaded. It would remind me that if I looked up 0.41 that way, I would have to put this as the value here. And then I would remember to do what to that number? 1 minus. We are finding the probability that a single x would score 21 or higher. And we would end up getting 3409, about 34%. Some people said, can't we look up the negative 0.41? And then you just get the answer directly, right? That's fine. You can work with your table in any way you want. You have symmetry. 0.41 to the right is the same as negative 0.41 to the left. Then you don't have to worry about a 1 minus. All right, so your answer to part A. There's about 34% of the students that score 21 or higher. Fairly likely to see a single student get that higher. What does it do in part B? Now you don't have one student, you have two. Two that are randomly selected, which means you have a random sample of size 2. That means those two observations, that first x and that second x, call them x1 and x2, they are independent of each other in terms of what their responses will be, and they are identically distributed, which means that model we just drew, that normal curve, and those probabilities apply to both of them. They both have the same model behind them. I want the chance that both will score 21 or higher. Both means and. The first person scores 21 or higher, and the second person scores 21 or higher. You've got the and between two different events that you know are independent. So by independence, what can you do? Multiply. By identically distributed, what are both of those probabilities? 0.3409. And then it ends up being that you just take your answer in A and square it. In the long notation, you're finding the chance that the first x is greater than or equal to 21, and the second one is. You would not need to write this all out. Just the answer in A squared is enough. And of course, then get that number, 1162. But because of independence and they're identically distributed, meaning the same model applies to both of them, I take the probabilities for each one, which are the same, and multiply. Now, you could have approached this as a binomial problem. You have a sample of size 2, and you have P, a success rate of scoring 21 or higher of 0.3409. And then what you're doing is you're finding the probability that both, that all 2 out of 2 are successes. 2 choose 2 is 1. Success rate squared, failure rate to the 0 because there are no failures. And you get the same answer here. So this is really a binomial problem, but it's doing the all versus the none. What if you had taken 3 people at random, and I wanted the chance that all 3 score 21 or higher? You would do what? Raise it to the 3rd. What if I took 5 people at random, and I wanted to find the probability of exactly 2? So now my sample size is 5. Out of the 5, you'd have to pick 2. Success rate, that 34% raised to the 2. And then how many failures would you have? Or 3 of them. It's a binomial problem. All right. So this question could be on the exam. It has to do with probabilities, normal curves, and independence. If you got A wrong, you forgot to do 1 minus, calculated your z-score wrong, looked up the right area for it but calculated z-score wrong, you'll get some penalty there. But if you took part A's answer, which is a probability, and squared it, you get full credit here, even though it's wrong on the answer key. We give you consistency. That usually helps rather than take away. All right, how about C? What's different in C? Random sample of 50 students. Now, if I had asked, what's the probability that all 50 score 21 or higher? 0.34 raised to the 50th, really small probability. Hardly ever going to happen that all 50 would score that high or higher. But that's not what it asks. It asks for what? The probability that the mean. Probability that the mean score for your sampled students, that is x bar. The probability that the sample mean would turn out to be 21 or higher. Now I need to know about x bar and what is its model in order to find that probability under its curve. What do we know about x bar? It was one of our results that we have up above there. Which result are we able to use? Number 1, that exact result, or number 2, that approximate one? Which one will we be using here? Did we have normality to begin with that we used in part A and part B? Yeah. We know by exact result number 1, x bar will be normally distributed around the true mean still, which is 18.6. But what's the new standard deviation that works for an average x bar? Take your original one and divide it by square root of n. That's your new sample mean standard deviation. So when you calculate your z-score and standardize 21 by the mean, that's the same, but the denominator is now with the correct standard deviation for an average, because averages don't vary as much from the truth. Individuals can. You can have individuals that score really high and really low, but averages tend to be closer to the true mean. And how much closer? Well, you get to divide by that square root of 50. You get a new z-score here. Now the z-score is 2.88. And now the process is the same as you did in part A. You're under a standard normal. You want the area to the right of this 2.88. So what will that probability be? If you look up 2.88, you'd have to do a 1 minus. And 2.88 would give you 99.8 as the area to the left. 1 minus that is pretty small. It is not likely that the average of 50 randomly selected students would be that high, of 21 or higher. 18.6 is what the true mean is. Averages of 50 people should vary around that true mean, and the fact that you aren't going to get 21 or higher kind of makes sense, that it wouldn't be that far away. Now, what we just found is another area under a different curve, this other normal curve. The picture that I drew in part A, I'm going to go back to for a moment. And this model right here is for x's, for individual ACT scores. What would the curve look like if you superimposed on it the model for x bar? It's still bell-shaped. It's still centered at 18.6, but what would it look like now? Much taller? Yeah? Less spread? Nope, I didn't change the color. It's going to. And the area to the right of 21, though, will be smaller. So x bar values vary less from the true mean. And therefore, the chance of seeing extreme values is not likely. All right, part D says, what if you didn't have a normal model to begin with? Would your answer to part C change? Well, what about A and B? Could you even answer A and B if I didn't tell you it was a normal model? If I only gave you the mean and the standard deviation for ACT scores, you couldn't answer those probability questions. You'd have to have the model, the density of some sort to find its area underneath it. But what about part C, which was about x bar? What does our famous result, CLT, say? Even if the original model wasn't normal, take a large enough sample size and the model for x bar can still be assumed approximately normal. And is 50 large enough according to our criteria? Yes. So our answer to part C, the only thing that would really change would be it's about 0.002. By the central limit theorem, we have n here of 50 is large. X bar will still be approximately normal. So our answer is approximately 0.002 for part C. We would be able to rely on the central limit theorem. We use that central limit theorem a lot. You're going to start to check for normality of your data by making a QQ plot. QQ plots will not always give you nice straight line, along a positive slope values, but you took 30 observations, so you're going to be okay. That's why a lot of researchers are told, you're going to go design a study, make sure you take at least 30 observations so you'll be able to fall back on that CLT if needed. All right, part A of your next question could be on Thursday night's exam. Draw me that picture, the model for flight time. This is a separate question that would be on the exam, and it would be having points that would include more than just the shape, but also labels and values. What model do you need to draw here? It doesn't say normal anymore, it says uniform. Uniform over the range of 110 to 130. That might earn me 1 point right there. Got a couple values in the shape. How about a label for my x-axis? It's the model for this variable x. Actual flight time. You could even include the minutes. I need some more on the y-axis. What am I drawing here? Generically, this curve is a density curve or a density function. It is the probability model for this continuous quantitative variable. Density is all you need, but then I need a value. And what would that be? 1 over 20, 0.05, found by the 1 over the base length. So base times height equals 1. All right, can someone tell me what the expected flight time will be? What's the expected flight time, or the mean flight time? What is it? 120? Midpoint? The true mean, or the expected wait time, is 120 minutes. That could be a part B question. Could you find the quartiles for me? Q1 and Q3? Could you find IQR, the interquartile range? All right. I'm going to give you the standard deviation, the value. There's a formula behind it. I'm not going to go through that. we are given that the standard deviation, sigma, and I'm going to give you its value, could the standard deviation be more than 10? If you had choices, 5.8, 10, 20, the only one that's reasonable, I hope? It can't be more than 10. 10 is your length from the middle to the end. And your standard deviation is supposed to be the average distance of the values from the mean. If you did 10, you don't have any values that are further than 10 from the mean, so how can that be the average? All the values are within 10, so your standard deviation should be less than 10. 5.8 is a number I'm giving you. Don't worry about where it comes from. I can give you the formula. It involves the 130 and the 110. But I'm giving you that so you can draw a better picture for part B. All right? So make sure you put a note. Professor Gunderson gave us this number, so you don't have to ask, where did this come from later? The formula is, for those who want to know, you take the distance, which is 20, and you square it, and you divide by 12, and that's the variance, so then you take the square root. That's how you get it. There's a formula behind it. All right, so we're going to take samples from this model, from this population that has this model. What sample size are we going to take in part B? Samples of size 100. Is that large? Yes, nice and large. We're going to compute the sample mean for each sample of 100. And we're going to do that over and over and over. And I'm going to start to make a histogram of those sample mean values, the X bar values. So I get my first one, and I put it on my axes. And I go take my next sample of 100 and get it, and put it on the axes. And I keep doing that over and over. What will that histogram start to look like? Will it look exactly like what you drew in part A? No. The only time you'll ever get part A back out is if you took samples of size 1. Because then you're just taking values from your population, and if you just plot them, they should start to look like the model that describes that population. But if you take samples of 100, what do averages start to look like for their model? Approximately normal. This is my smoothed out histogram rather than making an actual histogram. Where do you know it's going to be centered at? The true mean, mu, which is 120. And how about that new give or take? It was what before? I gave you it as 5.8. You get to do what? Divide by the square root of 100. That would be 0.58. Wow. So that first tick mark is at 120.58. The other tick mark would be at 119.42, and so on. Look how close your sample mean would tend to be to the truth. Suppose you didn't know what the true mean was, but you're taking samples of 100, and your original model was uniform. Well, from this example, I can see I'm going to get numbers for the sample mean that are pretty accurate at estimating that 120 here, the true mean. Averages do not vary as much as individuals can. Averages tend to be closer to the true mean than individuals. That's why I take a sample and not just one person's outcome and say, I think that's the mean. That doesn't make sense. Take a few outcomes, take 50 or 100 and average them. And now your answer for X bar should be pretty close to the true mean. So when you make an interval around it, you can be pretty confident about that range. All right, you get normality here. What's the main reason why you got to draw this picture? 3 letters. By the CLT. I think there's a song. Maybe. All right. We'll end with our last true falses. Part A would not be on Thursday night. Part B could. And then we'll turn to 2 questions from the review together. So look at A and B. Make your choice of true or false, and I'll get that up here for you to click in. Once we're done with these 2 clicker questions, we're done with clickers, and we'll turn to our review. Part A is up and ready for your answers. If we stopped after that first part, the central limit theorem is important in statistics. Yes, that's true, for sure. And does the rest describe what the CLT is? Central limit theorem is important in statistics because for a large random sample, it says the sampling distribution of the sample mean ends up being approximately normal. That is true. That's exactly what the CLT says in words rather than with a notation, but that's what it is. It's true. You can specify what kind of normal model, mu, sigma over square root of n, but this is what the CLT gains for us. All right? How about your second, true, false? Again, about sampling distributions. So when you're doing true, false, do you ever have a pattern that you think about, or it can't be all falses or it can't be all trues? Are most of you picking false because it has to be false since the first one was true? No? Good. All right, we get a split here of about 25-75. The answer is false, but you would have to explain perhaps why. Or maybe you could correct it to make it true. The very first line of my slide, the sampling distribution of a parameter. Do you have a sampling distribution of a parameter? Didn't we just do that question at the beginning? We identified the parameter, but it was the statistics that have a sampling distribution. That's wrong. The sampling distribution of a parameter is the distribution of the parameter value. There is only one value for any given parameter. That's a fixed unknown value. What would I have to fix in this statement to make it a correct one? The sampling distribution of, you could say generically, a statistic. You could give me a statistic we have studied, like p hat. And then you would say the sampling distribution of a statistic, such as p hat, is the distribution of the statistic values, the p hat values, if repeated random samples are obtained. And we learned that the sampling distribution of p hat, you had to draw it on Thursday night, would look like what? Approximately bell-shaped, centered at the true p. You've got a standard deviation that's on your yellow card. You might have to check the conditions if they are met for you to be able to say that. Very good. Time for review. Get out those lecture review. We're going to do number 1 and 2. If you don't have your copy, maybe your neighbor does, so you can take a look at them. Box plots in number 1, confidence interval in number 2. Let's take a look at number 1. These are questions from an earlier exam. They often, as you've seen maybe in those practice ones you're doing, have a final answer line just so we can zoom in on what your answer you're saying is. Maybe you did a little calculation over here, but you've got an answer. So we know what answer you're intending as the final one. Or circling, giving you some choices sometimes, so it's clear. We have, how old is your car? A study to compare the ages of cars found in a student parking lot versus those in a faculty parking lot. Random sample of 15 cars is taken from each type of lot, and the age is recorded. So what kind of study do we have here? We are recording whether or not it was student or faculty parking lot, student or faculty owned, and we're recording the age for these total of 30 cars. And our study is what? A designed experiment or observational? It's an observational study. We didn't actively impose ownership of those cars on students versus faculty or anything like that. We recorded the age and went to the particular spots and just observed. No active imposition or no changing or manipulation by the researcher in any way. All right, do you have then this car owner's status? Is it the faculty or student? And that variable, who owns the car, would be which role being played here? You've got age and you've got who owns it. Does who own it tend to influence the age, or does the age influence who owns it? Which way are you really looking? The owner should help to explain how old the car will be. Does age depend on whether it's a faculty or student-owned car? How about the type? Age. No, this one is car's ownership. It's either the student or the faculty. So that is what? It's not quantitative at all. It has to be categorical. I might record in my data set a 1 for student, a 2 for faculty, or some coding scheme. How about the other variable? Age. That would be the response. And age would be what? Definitely quantitative, right? Age of cars are usually only whole numbers, not fractions. I mean, there is a day it was produced, but it would probably be treated a little bit more discreetly for modeling. All right, what do we have next? Looking at our box plots. We have the box plot for the 15 ages of cars owned by faculty versus student. Watch that you go to the right box plot. Watch that you go in the right direction. If there's a word that's italicized or bold or underlined, it means pay attention to me. So you are led to the right place. Here we have the oldest car for faculty. Faculty. Oldest car, what should I say? How many years old? 7. I might get some say, if you ignore the outlier, it's 4. But why would I ignore the outlier? The outlier is there in the data set, drawn to my attention that it does stand out from the rest. There was at least one faculty member who had a 7-year-old car, maybe more than one, but at least one. And 7 years is the maximum. If I asked you for the range, you would take 7 minus the minimum, which is 0. The range of the car ages for faculty was 7 years, from 0 to 7. All right, going to the faculty side again. We have that one member was disappointed. 75% of the cars were newer than his. So how old is his car? So I know that 75 or 25 kind of question means either Q3 or Q1, right? And you try maybe both out, because it does depend on whether it's 75 or 25 and which direction you're going from that point. We want to take some age, and it's either Q1, which is what? 1, or Q3, which is 3. So let's try Q3, because that's 75%. I kind of think those two go together. And if I look at how many cars were newer than his, newer means younger, are there 75% here? Yeah. So his age of his car must have been 3. If I say 25% of the cars were older than his, 25% of the cars were older than his, what would be the answer then? Still 3. 25% of the cars are older than his, Well, you just said 75% or younger, 25% or older. So just be careful you're going in the right direction and make sure you've got that percent you want in that direction. It might take trying one and then seeing that it has to be the other. Part E talks about the students. And the first sentence there says the students' cars, they had ages that varied by about 2.8 years from their mean on average. What is that the definition or interpretation of? 2.8 is the standard deviation for the ages of cars in the student data set. So Joel's car is pretty new, only 3 years old. His z-score turns out to be negative 1.3. His z-score is negative 1.3. And how do you find a z-score again? You take the observation, which was 3 years old, minus the mean, which we don't know yet, over the standard deviation. And we're asked to find the mean. And I can't just find it from my box plot because where is that line drawn in the middle? That is not the mean necessarily, that is the median. And they may not be the same, especially if there's a slight skewness in that distribution. They might not be that far off, so I can go back and check that later. But if you solve for the mean here, what do you get? About 6 something? About 6.64, using these actual numbers there. And if you go back to your box plot, does it look like it could be about 6.64? Median is what there? What was the median? 6? And do you remember on the Sunday review, there was a question, is the median going to always be the midpoint of Q1 and Q3? Here's Q3, here's Q1. Is that right in the middle, halfway between? No. The median will always have 25% between Q1 and the median, and 25% between the median and Q3, but that midpoint will not always be where the median sits. All right. And our last question has to do with a confidence interval that's already been computed for us for estimating the proportion of all college students that own a laptop with 95% confidence. The interval's already calculated, so it was calculated using what formula? It doesn't say conservative one here, so it must have done it with what? P hat plus or minus your z star, and then you've got some kind of standard error. That's the general formula from your yellow card. That was used to get this interval. My first question is to give me the proportion in the sample that said they owned a laptop. I'm asking you to give me what quantity? By symbol it is not x bar, but p hat. P hat. Give me the proportion of the sampled students that said yes. That is, give me p hat. How do you find p hat? Is p hat in your interval? Is there a 95% chance that p hat is in your interval? It's a 100% chance. It is. And where is it in your interval? Right in the middle. P hat was where you started and you went out plus and minus from it to form your interval, so p hat is the midpoint of this interval. My interval goes from 82 to 92, so that's a 10 full range, so what must it be? The midpoint, which is 0.87. Take the two values and add them up and divide by 2. Or because it's 10%, I know I have to go 5 to get to the middle. What was the margin of error? Without computing it so much, 5%? What did you have to go from the middle to get out to the ends? 5%. So could you probably work out the standard error by kind of a little bit of algebra? So I didn't give you the sample size to compute this margin of error. I do know the z star would have been 1.96, but I couldn't actually compute the margin of error except that I got it from the interval, where the width is 10, so the margin of error is 5. Which of these two statements is the correct statement for interpreting the confidence interval? We can be 95% confident that between 82 and 92% of all sampled students own a laptop, Between 82 and 92% of all college students own a laptop. Number 1 or number 2? Number 1 is wrong because p hat is in there. I'm not 95% confident, I'm 100% confident p hat is there. I want to have confidence that the true p is in that interval. Would you be able to interpret the confidence level too? That could be asked also. All right, you've got an exam on Thursday night. I will see you Thursday for a little more new but also review.